very, very important, timely topics related to soil and water for the state and beyond. And today's guest is no different. Kevin Kuehner. We'll be introducing him in a little bit. We are really excited to have you here, Kevin, and we'll hear from you soon. The other part I want to make sure that we recognize is the members of the committee. It takes a big effort to put these lectures together. And so I would like to recognize, and if you are here in the room, if you could just kind of wave your hand. Ren Daswell, sorry, from USDA ARS, Diana Kerwin from Forest Resources, Joel Larson, I don't think Joel is here. Lindsay Peace from Soil, Water, and Climate. Carl Rosen from our department. Gary Sands from BBE, I think he's here today. Jeff Strock from our department. Melissa Wilson, also from our department. And then we also have Ariana Redig and Nora Poole and Kerry Jargo that have helped us tremendously every year. Without their support, all their, the technology, all the preparation for this meeting, it could not be possible without their help. So let's give them a round of applause. And now I would like to turn the time over to Mike Schmidt. He's the Associate Dean and Department Head of, I always forget the name, FNR. It's not FNR anymore. Anyways, I need to read it. Anyway, Mike is here. He's a member of our department and also in the Dean's office, and he will give a quick update and a few words. And then Brent Williams will give also an update from the department.
Thanks, Fabian. And this is going to be brief. You didn't come here today to listen to some administrator. I know that. I'm Mike Schmidt, Associate Dean at CFANS, and I'm maybe more proud to be having roots here in the Department of Soil, Water, and Climate back when I was a faculty member. It's a privilege to represent CFANS and to say thank you to everybody that's here today for this lecture series. The Larson Allmaras lecture series is something that I see every year, and it just brings back wonderful memories of two really outstanding humans. Bill Larson was the department head that hired me and took a chance on me, and I'm thankful to him. And Ray Allmaras is someone that, he would come wandering down on second floor over the soils building with a kind and gentle approach and just exude wisdom to all of us. And it was so comforting to be in a conversation with Ray on a regular basis. So just two great individuals, and sincere appreciation for those families and supporting this lecture series. It means a lot. It brings the community together, the soil, water, climate community together, and I think that that's extremely important. Update from the college, there's not much to say. We're weathering some storms right now, funding storms, et cetera, and our radar isn't working. We don't know what's happening one day to the next, but we've got a land grant mission that we're following. We're taking, steps to keep things going as they should be for all of Minnesota and beyond. So that's where I'm going to stop that right now. Not much else to say there. Rest assured, though, Soil, Water, and Climate and Brent Williams is doing just a great job, truly respected down at Coffee Hall with the administrative team in that. And he is the best advocate a department could want. So you're in good hands with Brent. Down from a CFANS administration perspective. Final thing I just want to say, I'm looking forward to Kevin Kuehner's talk today. And I hope you are too. This is a topic. I was a nitrogen researcher, so this really hit close to home for me. And I've had the privilege of overlapping, in our work with Kevin for years, and I have great respect for the work that he's done. And I'm truly looking forward to your presentation today. So, let's listen well when he gets up here. So that's it for me. I'm done.
Thanks, Mike. Thanks, Fabian. Yeah, so Brent Williams. I'm the professor and head of the Department of Soil, Water, and Climate. Thanks to everybody for joining us here today. I'm going to give just sort of a summary of what's been going on in the department, hit some highlights, and maybe end with a little bit of the storms that Mike alluded to that we're trying to weather here. Try not to get too doom and gloom, but definitely want to make sure we're addressing that. So I want to start with our current 24-25 recruits of new grad students that joined us between last semester and this semester. And our graduate program is the Land and Atmospheric Sciences, LAS program. And it was a really great year for us. We have 14 new graduate students across master's and PhD programs. This was an exciting year, and there's a lot of new energy that came in with these students. And I'll also just briefly mention, I'm going to say quote numbers or anything, but our undergraduate programs, we teach mostly in the we have a soils program, and then we have an environmental science policy and management program that we do a lot of teaching for. Both of those programs, enrollment is up at the undergraduate level as well. So even though university-wide and sort of across colleges, there's recruitment and enrollment sort of issues looking forward, our programs are continue to grow. There's a lot of interest from our future scientists in our research areas across soil, water, and climate. I wanted to recognize this last year's some of the graduate student scholarships that went out, and definitely recognize the different families that support these various fellowships, endowments, and funds. I also wanted to maybe just take a moment right now, is looking at some of these previous connections in the department. I see a lot of emeritus faculty. Could emeritus faculty in the room stand up and be recognized, adjunct and otherwise? Great, thank you. Maybe a raise of hands if you have a past degree or current teaching in the department, doing research in the department. Thanks for joining us. It's our alumni. I'm going to highlight a few different recent awards that some of the recognition that's going out currently for folks in our department, starting with our Soil, Water, and Climate Diversity, Equity, Inclusion Committee. So this is an interesting time where this topic is becoming taboo. We are an interdisciplinary department, and in the roots of that, diversity across all definitions of diversity is sort of at the core of what we do and what we're always going to do. And our committee takes this work to a level that inspires what the college is doing, what the university is doing. And this committee, past and current members, are being recognized this year from the college for an Inclusive Excellence Award. So we're really excited about that. Another award I want to highlight here is Carrie Jarko. Where's Carrie right now? Did she sneak out? Yeah, okay. So this shows why Carrie is the 2025 Borealis Exemplary Staff Award. She never sits. It's hard to. I don't know if I've seen her sit down for more than a minute at a time. And this last year we went through a big administrative change in the department structure, and we were down to basically Carrie doing all the administrative duties of the department, wearing about 5 different hats. So I'll show you where we got to. We're in a better place now with new hires, new members in our administrative team, but you can see sort of the breadth of what Carrie was covering, and the very deserving of this recognition. Anna Cates, who's in the room here as well, is going to be recognized next week with the 2025 Outstanding Extension Faculty Award. Jake and Bob are recently recognized with Watershed Innovation Grants from the Water Resources Center. Congratulations to them. GP, I think I see GP, yeah. GP Singh is just received a very competitive fellowship to get. It's recognition through the graduate program for a doctoral dissertation fellowship. So congratulations to you. So members of our soil judging team aren't with us right now because they're out in the field. Oh, you're back.
No.
Or you're the other part of the team.
We went to the past competition.
The-
75% of the team is at
Okay.
nationals.
Okay. Okay, yeah, so there's a regional competition and a national competition. So this week in actually Kevin, at your alma mater, it's at Wisconsin, Stevens Point this week is the national competition that our soil judging team is competing in. And you can see it's kind of the activity of this team and their sort of their placements. I'd say even more important than how the team places, this is a really critical program that a lot of the alumni that are a part of the soil judging team end up following careers in soil and water. This being a part of this team and program really connects people with lifelong interest in this topic. And so this is why this is such an important team for us in the Soil, Water, and Climate Department. They're doing great on fundraising efforts. They're doing a lot of social media things and being recognized for the work that they're doing there as well. So we're really excited about that. And please, those of you that are longtime givers, please continue. And if anybody wants to learn more, we can connect you with opportunities to help that team. I won't go through each position, but this is where we're able to build up to for our new administrative structure across all of our pre-award and post-award work that happens, our communications work that happens, our graduate program, our administrative director and administrative coordinator. So Ariana, Kristen, Chana, Carrie, Nora, Amber, and Sue are our team. And like I said, Carrie was doing other than the finance part of it, Carrie was doing a lot of most of this at one point in the last year. So, but welcome to the new members of the team. All right, so this is the first official announcement of this. I haven't shared this with the community yet, but we have 6 successful promotion cases in our department this last year. I don't know, Mike, if you know if that's a college record to have 6 out of a department, but I think it's close. Yeah. So you never had that many? 4 is the most. Okay, so Carl has 13-year history before, and this was never quite this many. So, yeah, it was definitely a team effort, but obviously, you know, the great work that these people do is you know why all these cases are successful. So Anna Cates, I'll note that Lindsay Pease, who's also in the room, Lindsay received tenure and promotion to associate level. Congratulations. Heidi Roop also received tenure and promotion to associate. And then Satoshi, Dan, and Yushin all went up to full professor this last time. So they'll also be recognized next week or the week after. Next week in a ceremony, provost ceremony. Yeah. And also at the college program next week as well. So congratulations to all 6 of you. Major accomplishment. Okay, so yeah, transitioning to some of our future planning as we think about look back at this last year and look at some of our retirements from the department. So Tracy Twine, Jay Bell, and Peter Snyder were all faculty members who retired over the past year. And I also wanted to highlight Tom Graff, who works at our soil testing and research analytical lab. Retired this last year, and Tom had been here for over 50 years. So quite the service to the department and the Strahl research lab. We are hoping we've had something like 6 retirements in the last several years without a lot of replacements. And so that's something we're working on is what are our critical replacements for faculty in the coming year. All right, and this is our big this is our big news. I want to take a moment to share this with everybody. Our USDA ARS Soil and Water Management Unit, which both Bill Larson and Ray Allmaras were members of over the time span shown there. This unit joined with us on the St. Paul campus in 1961, so 64 years of partnership. And in that time, we trained across co-advising. All the scientists with the unit act as adjunct faculty in the department and advise and co-advise graduate students. So over 50 graduate students have earned degrees through that time as a partnership between the department and the ARS unit. So there are 6 scientist positions in this unit. And here you can see that 5 have recently announced retirements and deferred resignations based on circumstances of alternate options going forward not being very rosy. So 5 of the 6 scientists are no longer with us, and their last day was on Tuesday. There are a number of other technicians, research staff, postdocs that also left with a deferred resignation as well. So this is a real major hit for us in the department. We do active research, active student training across the unit, the department, and those positions are technically still there. The unit still exists. Brent Dalzell is our remaining scientist running a team, and just received a whole bunch of extra weight on his shoulders. But we here as a department are going to stand with trying to maintain that unit, and hopefully, when allowed, that we can build that unit back up. That's our hope. We on Tuesday had a sort of a luncheon to sort of bid farewell to everybody leaving, and I want to just kind of highlight that I already pointed you out, Brent, but this is the science unit currently. So, but you love that attention. So that's clearly a major thing. I'll also point out that Josh Gamble's with us as well, is in the plant science unit, but works very closely with the department as well. So we have these 2 scientists and these 2 units that are still really connected with our department, and we'll hope to work together to build out the future. This work's too important to let it go. Yeah, so maybe before I get to my last slide and then hand over back to Fabian, I just want to say that, in addition to losing our USDA colleagues, we do have a lot of federal funding that's frozen right now across different agencies, federal agencies. And some of those may continue and go through, but we don't know exactly yet. So there's a lot of anxiety right now in the department, but everyone's holding on to hope that we can pivot and move forward. That funding, I just want to really point out that that's the funding that trains the future generations of students and leaders in our department. That's across soil, water, and climate, environment, and agriculture. This research leads to sustainable practices for clean water, clean air, and especially healthy soils coming out of our department as well. So much of the legislation that led to, like the ARS Soil and Water Unit, for example, and a lot of the funding that comes to our research programs goes back to the Dust Bowl of the 1930s. So this is a picture of the event, April 14th, 1935, so 90 years ago plus a few days. This was an event that happened while Congress was meeting, and it sparked the first legislation. You can see later in April 1935, Congress officially established a Soil Conservation Service, which eventually became the NRCS. This work, it eventually led to a lot of the various conservation efforts, a lot of the soil health efforts, water resources like we're talking about here today. I wanted to sort of conclude here with this quote from Kuehner Bennett. Does anybody know who Kuehner Bennett is? Few people nodding yes. So he testified at this 1935 hearings and helped establish this first conservation effort and became the initial director of that program as well. So had a kind of a famous quote that said, if you take care of the land, and the land will take care of you. So I think that's really what we're looking at today, is that we don't want this, we don't want to get to a point where you know, if we divest at this point, we definitely we risk sort of history repeating itself. And we know what happened historically. We see through images what it was like when we didn't take care of our land and our water and our air, and we just can't let it get to that point. And you know, if you want to know what the world was like back then, I've been listening to a lot of old Woody Guthrie songs. So those of you that know Woody Guthrie, even those of you that don't know Woody Guthrie, I encourage you tonight to, there's a Dust Bowl Ballads is a collection of a lot of the Dust Bowl songs from Woody Guthrie. And it kind of describes what society was like at that point. So we definitely don't want to return to that. All right, with that, I'm going to hand it back to Fabian.
And before we do the introduction for our speaker today, I just want to recognize two of Ray's sisters are here now with us. Lauren McMoonan and Camille Lex. And Mike and Jen Strally, Ray's nephew. Here. So now it's my great pleasure to introduce Kevin Kuehner, our speaker for the lecture today, our guest speaker. Kevin is a hydrologist with the Minnesota Department of Agriculture based in Preston, Minnesota. Kevin has a degree in water resources management and soil science from the University of Wisconsin-Stevens Point, and has over 25 years of experience leading and managing collaborative water quality projects, fostering partnerships with farmers and stakeholders. His work has focused on addressing the challenges posed by agricultural contaminants in surface water and groundwater, particularly in the southeast Minnesota karst region. This area is known for its complex geology, which makes understanding groundwater pathways and water quality improvements a significant challenge. Throughout his career, Kevin has been instrumental in helping advance practices that protect water resources and maintain agricultural viability in Minnesota. The title of his presentation today is Improving Understanding of Groundwater and Nitrate Trends in Southeast Minnesota. And with that, Kevin, please take it away. We are all looking forward to hearing from you.
Good afternoon. Yeah, thank you so much. This is an absolute honor and privilege to be here. And to be honest, Fabian, you know, when you send that email to me that I was invited to this, I had to read it at least 2 or 3 times just to make sure that you had the right Kevin. Because I just literally probably like 3 months before had the chance to go through Sylvie's presentation that was presented last year, and I really enjoyed that. And it's just really uncanny to see that your email come through. So really appreciate it. Thank you to the committee. Really appreciate the nomination, and thank you to the Larson, Allmaras families. It's a privilege to be here. So today my focus is to talk about groundwater, and specifically the area that I work in, which is in Southeast in the karst region. And I've had the really fortunate opportunity to work with 2 really great researchers on this. Tony Runkle, who's here today, and also John Barry. And I'm basically gonna represent that team and that collaboration and kind of share a lot of the data from this paper that was just recently published in January, getting at these questions about the groundwater age and how do we interpret what's going on with regard to nitrates down there. Before I do that, I'm just going to kind of set the scene a little bit, because really to understand nitrate, we have to understand groundwater. And I'm going to kind of set the scene a little bit and kind of set us up for that. At the end, I don't want to leave us just hanging either. I want us to kind of, also want to kind of share some case studies of what farmers and stakeholders and our partners are doing on this issue related to nitrates. So some pictures here kind of setting the scene for the southeast corner of the state. This is a very interesting part of the state, very distinctive in terms of its geology and its water resources. And, you know, from the kind of bucolic bluffs and ravines and stream valleys to caves to the cold water trout streams that we have. This is a picture, I wish this is a picture of me. This is a picture I took of my son. We fished about 3 weeks ago on a river not too far away from us. Not going to tell you the name of it. But just incredible brown trout in there, just really fat, really healthy looking. And we had some that were 18, 20-inch size brown trout. And this is a natural reproducing stream of brown trout. And I think they were just really hungry that day. And we were really lucky to land a lot of those. This area is also really renowned for its really productive silt loam soils, well-drained silt loam soils that are exceptional yield potential. And, you know, looking at this picture, we've got that really nice strips of alfalfa, and it looks like we got some baled soybean stubble there, and then the corn. And that kind of tells us that, yeah, this is livestock is also very important to this region. And, you know, a lot of farmers, of course, erosion has always been a concern for them, and they're used to, you know, dealing with that and managing that. But what I've been working with, especially since I've been down there for almost 18 years now, is these are kind of the big four that I really focus on when I talk to farmers in terms of what we're trying to really focus on here. And it's this balance, right? It's this delicate balance that we're trying to produce of producing our food and also protecting the water that we drink. And these are the big four that I talk about. We talk about the runoff, the volume of water running off of these fields. As one of my farmers likes to say, he says, I'd like to see that water walk instead of run, in terms of, you know, anything we can do to make that water infiltrate rather than run off the surface. And then with that runoff, we have sediment and attached nutrients like nitrogen and phosphorus, of course, and then also pesticides, both in surface runoff and in groundwater. And then that big one there on the bottom, which I'm going to focus our attention on, is nitrate in groundwater. We do a lot of studies in the Southeast. We're fortunate to be able to do on-farm demonstrations, and that's a picture there of one of our edge of field sites that I'll be talking a little bit about here in the next few slides. But time and time again, when we do all this monitoring, you know, ultimately it comes down to the farmers and landowners and the homeowners asking us, is the water quality getting better? Or is it getting worse? And where is it getting better? And where is it getting worse? So those key questions that come up often is, you know, where is nitrate trending? Where is it getting, where is it going up and where is it going down? And it's one thing to do all the statistics and all the data management, the data science to get at that question. The hard part is, how do we interpret it? And especially within the context of the complex hydrogeology that we have in the Southeast. And then that last question is, how soon can we measure that water quality improvement? And especially we're in halfway roughly through the Clean Water Fund right now. And, you know, that question is going to be more and more important as we move forward over the next 10 years, as we get close to the end of that Clean Water Fund. And to answer that question, it's kind of like you have to kind of throw up your hands sometimes. We often get calls from farmers or landowners asking what we're finding with the water quality data. And I go through this kind of long explanation and try to explain it. And then I get off the phone and I'm just like, God, was that helpful at all? Did I help that person at all? And I kind of punted, you know, in terms of how do we answer that question? And where we struggle is this question of, well, we really need to know how old that water is if we're going to really try to answer that question, especially in well water. But we also have to understand the entire system, right? Not just well water, but also the groundwater that comes out of our, that emanates in our streams and in our springs. Basically, in Southeast Minnesota, 80 to 90% of that flow that we see all year is groundwater to that stream. So when we talk about groundwater, it's really challenging. It's something I think we often sort of just not talk about too closely because we don't understand it very well. And it's hard to educate it, right? Because it's something that we can't see, we can't really visualize it very well. But in the Southeast, we have an abundance of springs. And this is a spring called Winnebago Spring, and this is flowing into Winnebago Creek. This is in Houston County. And what I like to tell people is, this is the point where you're seeing, groundwater become surface water right before your eyes. And it's that invisible becoming visible. I've had the opportunity over the last probably 6 or 7 years, I've been invited to speak to the 6th grade environmental field day that they have every year, and it's located here. So my backdrop is this spring, which is just a great site. And the kids, the 6th graders, there's I think 6 or 7 classes consisting of about 30 kids each, and they travel to forestry, wildlife, soils, and then my stop is groundwater, fossils, and geology. And I always, every time I do this, I just have an improved respect for teachers, and especially as you go through, cycling about 150 kids over, a few hours. And but it's really fun. I really enjoy it, and you get some really interesting questions. And the first question that typically they ask is, how soon can we jump in the water? And then number 2 is, can we drink the water? And then number 3 is, where is that water coming from? And we have another spring. This is called Big Spring, and this is in Beaver Creek Valley State Park. If you've ever been there, if you haven't been there, it's a small park in Houston County, just north of Caledonia. And if you travel all the way in the upper end of the park, there's a spring that's called Big Spring. It's one of probably 6 or 7 different springs called Big Spring, very common name. But it is the kind of the headwaters for that trout stream in that park. And I think it was, 2009, they put up, the Minnesota Geological Society put up a rock and a sign, a plaque on that rock. And then in that plaque, they say, water bubbling out of the ground is a natural wonder. Where does it come from? How long has it been in the ground? And then that sign goes on to say that they're kind of speculating, they're kind of estimating this, but they're saying that they think the water coming from Big Spring has not been in the ground for a long time, and most likely less than a year. So they're getting at that question of, the age of that water and trying to, conceptualize that a little bit. And, probably for the time, that was the best that they kind of were estimating at that age. So we're going to come back to this. I'll come back to this at the very end, and we'll see if that may have to be modified or edited. So this is the paper, like I mentioned. Again, I had the really fortunate opportunity to team up with Tony and John. And Tony is the lead geologist with the Minnesota Geological Survey. He's been there for over 30 years. And then we have John Berry, who's with the Minnesota DNR. He's a hydrogeologist, and he's in the GeoAtlas program. And again, very fortunate to be able to work with them on this project. This is kind of building off of other acknowledgements here with other people that have kind of, in one way or another, really helped with this project. Particularly Holly Johnson for helping with some of these graphics. John Niebuhr, who's here today. John was really instrumental in kind of assembling us as a small team of different people with different expertise to get at some of these questions and provide some of the initial funding through the Environment and Natural Trust Fund. Also want to recognize the USGS, in particular Jared Trost and his team, for kind of really helping us with some of the atmospheric tracer data that we used for this study. So let's get back to the nitrates. So this is a map across the whole entire state showing the results of the initial township round of sampling that was done by the Department of Agriculture. This was done from 2013 through 2019. It really represents probably the most comprehensive nitrate analysis that was done across the state. And this is really intentional in terms of where they did this sampling was in areas that had a high percentage of cropland and also a high vulnerability to nitrate in detections in groundwater. And so what you're seeing there in red are the areas that had 10% or more of the samples above 10 milligrams per liter. So those are sort of the high nitrate areas that we wanted to kind of focus in on. And if you look at statewide, about 9.1% were above 10 milligrams per liter. The 10 milligram per liter mark is what the EPA uses for the drinking water standard. And the science that goes into that is that the concern about that is that if infants, especially less than a certain age, especially around 6 months or less, if they ingest nitrate, what that does is they don't have the bacteria like we do in our stomachs to process that nitrate, and it reduces their ability for their blood to carry the oxygen. And so it results in methemoglobinemia. If we look at the southeast area, the driftless area, we see that our nitrates are a bit higher, about close to 14%. So let's talk about why that might be in terms of the geology and the landscape. So if we look at this map here, this is showing the last glacial extent about 18,000 years ago. We see this area that really kind of missed out on that last glacier. And we can see that really well in the topography here. This is just showing the contours and really showing where that steep topography lays here in this region. Wisconsin probably can claim that actually this is their true driftless area on their side of the river. Minnesota, Iowa, not so much. Probably it was impacted at some point in geologic history that we had some impacts from glaciers, either direct or indirect. This area is known for its karst. Karst is a landscape with distinct hydrology, landforms that occur when underlying rock is soluble. And we have distinct features that we can find out there, like springs, sinkholes, and caves. The other aspect of karst is that the depth of bedrock. We actually have quite a bit of karst throughout southeast Minnesota, but most of it is covered by that thick glacial till that was deposited in glaciers past. So over 50 feet to over 100 feet of glacial till over those features. But this area in red, those are the areas where we have that thin soil. So those less than 50 feet over that fractured bedrock. So not much filtering ability if we have that only thin soils over that area. And we can visualize that with something like this. This is a picture taken by Martin Larson 2 years ago. This is kind of near Interstate 90. And this is a recently harvested hay field. And what you're seeing basically is the expressions of that fractured bedrock and how close that bedrock is to the surface. So all those sort of hatch marks are indicating where the soil essentially has over the many years has infiltrated some of those vertical fractures and it filled them with soil, and the alfalfa is looking for moisture and it finds that moisture in those cracks. And that's what we're seeing in those signatures there. But that depth of bedrock can be quite variable, and like anything with our environmental data is quite variable. But this is some imaging that we did. We worked with Dr. Toby Dogweiler when we started one of our Edge of Field projects, and we wanted to know the depth of bedrock. And so what he did was called electronic resistivity imaging, which basically is sending current through that soil and measuring where there's high resistivity and low resistivity. And the low is kind of showing up here, can be interpreted as clay or till materials. So you can see there that we have, in this particular field, we have less than 15 feet of distance between the bedrock. And we can also see a really clear signature there of a black area. That black area kind of looks like a little bit of an eyeball area there. And that's actually a signature of a sinkhole. And so really that's kind of open void space. So there really is no material in that area. And so that's the signature that's giving off. And we can go about a mile away just to the west, and we can find fields that have depth of bedrock that are a little over 30 feet. And so you can imagine the nitrate is going to move, quite differently between these two different fields, just based on, the thickness of the clay deposits versus depth of bedrock. As I mentioned, sinkholes another feature, in this landscape. And the thing I want to kind of point out are sinkholes are not the primary pathway for nitrate. that pathway is really through leaching through this entire landscape. One thing, that caught a lot of attention in the 1980s, especially, was this concern about people dumping, materials into these sinkholes, things that really shouldn't be in there. The good news is when you look at these sinkholes, you don't see any new garbage, which is really good. I think that education really helped pay off, that people start to understand that there's this connection between this and groundwater. So nothing intentional, but sometimes there can be unintentional situations like this. And this is a farmer had sent me a picture of this when I first started working with him. He says, sinkholes, yes, I have lots of stories about sinkholes. And he was going out to spray his cornfield. He drove up his grass waterway, and then on his way back, this sinkhole collapsed under him. And this is a classic example of a cover collapse sinkhole. And fortunately, in his situation, it wasn't very deep. But sometimes when these can happen, you can easily have over 30 to even 50 feet in terms of a straight drop down. And fortunately, also, he was empty with his spray tank. And, fortunately, none of that leaked. But you can imagine if that would have leaked, that would have been in the sinkhole. And typically what happens is this would either show up potentially in a shallow well that might be in that area, or it may show up, well, for sure, it's going to show up in the nearest stream. And we have a dye tracing that DNR has done that shows that shows up within hours, typically. So why do we have all these features in the southeast? Well, it really boils down to this chemical reaction that's occurring with the rock. So we have calcium carbonate that interacts with slightly acidic water, whether it be in the rainfall or within the soil, and that produces carbonic acid. And that reaction essentially dissolves that calcium from that calcium carbonate and dissolves it and weathers it and removes it away over the system. And we can have what's called kind of solutionally enlarged fractures. So we have that initial fracture, but thousands and thousands of years of that water interacting with it makes that fracture larger. And then we can have, of course, anything, if you've ever been in a cave, that's what you're seeing, that process occurring, but at just a much greater scale. So again, we can't talk about nitrate without talking about the geology and how that moves in the system. And this is basically a basic cross-section of southeast Minnesota, showing you all those different layers of rock and also where we get our water from, those aquifers. The white is showing basically where most of our groundwater is coming from in the southeast. So the St. Peter, the Shakopee, the Jordan, Lone Rock, those aquifers are very critical for the groundwater in that area. That's made up of, highly permeable sandstone and limestone. But what's also really important to note on this, and this is where Tony has done a lot of great research and a lot of work on, is really helping us better understand these aquatards. And aquatards are basically these areas that limit the downward movement of water and make that water essentially go horizontally in many cases. And this can be made up of primarily, siltstone and shale, but it can also be made up of carbonate rock and also really fine-grained sandstone. And as Tony will tell you, all of these aquatards are variably leaky. Some of them are very competent, and some of them, like the Oneota, for instance, is not so competent, and it can be variably leaky through it. A good example of the Decorah Shale is where it's pretty, very, very well competent, especially if you get away from those deeply incised valleys, and really dictates essentially where that water is going to move. And this results in a pronounced stratification of groundwater age and basically the contaminants, that we end up measuring in the water. So this is a little bit more complex. I'm not going to spend too much time on this, but I'm just kind of now layering in the hydrogeology. Once we have that water saturated with rock, that rock saturated with water. And this is a cross-section kind of looking from Mower County all the way to the Mississippi. So over 3 different counties. And it's showing you all those different layers of rock, like what I showed you before, but it's also introducing these arrows showing, where you have kind of that recharge to the water table, and then those straight arrows representing that predominant flow of where that water is eventually trying to move. And, that water is moving wants to get from the highest location to the lowest location. It's also moving under pressure in some of these areas, but ultimately a lot of this water is ultimately trying to get to the Mississippi. But then we also have a divide where some of it's kind of going towards Iowa. It's really a complex system. You can imagine this at this scale, imagine that even a finer scale. And so many times I get questions again, from landowners and farmers saying, why does my well have high nitrate, but my neighbor's has, no nitrate at all? And again, I always struggled with trying to answer that. And I always try to say, well, I'll get you this far, but let's have Tony and John maybe explain a little bit more. But we can't rely on them all the time. And so the idea was, can we bring the geologists to the masses? And so about 7 years ago, I pitched this idea of creating some educational videos and graphics that can help convey some of these really complex interactions, but do it in a way visually that we can understand it. We were fortunate to get a really good graphic designer. And actually what we did is we collected drone imagery of actually cross sections throughout Southeast Minnesota and integrated those into these. So these are actually pictures that are then embedded into these images. We kind of at the last minute, we decided, we created these posters as well. And then we thought, maybe we should just create a really short video that describes, a 2-minute video. And this is the one that has got the most views so far. It's close to 200,000 views, and been very, I think, very useful for a lot of schools when they talk about groundwater and they say, hey, we have to talk about groundwater in our course. This is where they start. They start with this video. So next thing I want to talk about is to really get at these questions, the importance of scale. And I can't emphasize this enough, because are we talking about the field scale or are we talking about aquifer wide scale? And the field scale is hard enough a lot of times. And I'm looking at many people that have done a lot of work on that over the years. It's hard enough sometimes to get good data out of the field scale, nonetheless, then go to the bigger scale at the aquifer scale. So let's start with the hardest one first, I guess. So let's look at the nitrate trends that we've had. So this is a lot of data covered over 3 kind of different scales here: wells, streams, and springs. It's over 1,100 sites, 35,000 samples. Primarily reflects data from 2000 to 2021. The significance was considered when the p-value was less than 0.05, using non-parametric methods to come up with these statistics. You'll notice that the wells, we have a kind of predominant amount of wells that are showing no trend or non-detect. And I'll kind of get into that. It really kind of depends on the data set when you start to analyze this data. And I'll get into that a little bit more. But with streams and springs, it's a little bit more easier to kind of paint this a little bit more with a broader brush. But we notice that the streams and springs all have a predominant or dominant increasing trend on those sites. So let's focus on the spring sites first. And this is what the data typically look like. So I just took an example from each of those. Fountain West and Amherst, those are considered like our water table springs, so the uppermost aquifer. And we see that the nitrates are highest in those. So they typically are around 10 milligrams per liter. We see in Fountain West that it goes up and down, but it's really wild in terms of its the variability. And really no trend. We look at Amherst spring, and this spring is actually going down, or appeared to be going down during this time period. Highway 76 spring, though, it was very clear that this site is showing an increasing trend. And it's increasing at a rate of about 4% per year. So that would equate to about 0.2 milligrams per liter per year. So, and to exceed the 10, if it continues to move at this current pace, we're going to exceed the 10 milligram per liter mark in about 23 years. So the question is, why is this happening? This is something that Tony and John and I have struggled with, how to really effectively understand and interpret what is going on here. Because the challenge is that the difference is when we really start looking at the land use data, we know that it's not attributable to that alone. We know that there's other factors, other variables that is probably explaining that. So it was hypothesized that the variable mixing of that local and regional groundwater with different ages is really that key factor. And ultimately, it comes down to those interpretations are really confused and confounded by a poor understanding of the groundwater age or the residence time. So what do we mean by residence time? So residence time is that total amount of time that it takes for rainwater, snowmelt, as it infiltrates that soil surface, to travel through that unsaturated zone there and make it to the water table, and then eventually get to the point that we're sampling, whether it be a well, a spring, or a stream. In this case, I'm using an example of a well where we have that interval down there at the bottom. And then there's different terms for residence time, travel time, lag time, age. You'll kind of hear me use those words interchangeably. They're kind of the same for the purposes we're talking about. What's really complicated in the Southeast is if you look at a rock face and a quarry, and you see all those different fractures and various things that are going on there, it's called a triple porosity system because we have kind of 3 different main pathways that water can go. Some of that can move very quickly through these conduits or bedding planes, essentially, that move that water like pipes through the system. We have fractures, these vertical fractures that can move it really quickly from the surface down to those areas. And then we have that matrix, the amount of water that's stored within those really tiny pore spaces of the rock. All of those confound, our interpretation of these data. The other aspect of this is residence time is that, that single drop of water that we collect from let's say a well or a spring, it's not just one age. So that single water may represent a mixture of different ages. And kind of going off of Jared Trost, kind of a spin-off of, he had a really nice graphic kind of showing this, and this is sort of inspired by that, but it kind of basically just shows if you have, you'll have some really fast flow. The animation's not working here, but if you have really fast flow, of course, you're going to have it come to the screen interval, and some of that water, those particles of water are going to move, quite quickly, to that well. And so USGS uses what's called a lump parameter model to estimate that amount of fraction that might be younger, that might be older, and ultimately trying to estimate where's the bulk age, what's the kind of where most of that water, the age resides. This sort of same process works for springs. It also works for streams, except for springs. We kind of look at springs as being kind of an integrated average of a lot of different flow paths to that system. Whereas a well, a well is intentionally drilled to avoid contamination. So it's going to tend to have much longer residence times and also, less contaminants in it too. This is a graphic I like to use. This is from USGS, kind of just simply showing that we can have a range of ages. Again, kind of showing that where that younger water can be above those confining beds or aquatards, and much older water as we get deeper in the system. So we would expect, theoretically, that as we go down with depth, our age will increase as well. So how do we actually measure this and actually quantify an actual age? If you're interested in that really fast flow water, DNR uses dye tracing. That's kind of one of their main tools for that, where they place dye within a sinkhole or a dissipating stream, and then they place charcoal packets at various locations, and they analyze those charcoal packets to measure where it actually comes out. If you're interested in more of that years to decades old water, we have to get much more sophisticated, and that's where USGS has developed several different methodologies that have been used for quite some time. And it's basically using, tracer information that is from us, from our activities. One of them being tritium, tritium is a natural product in the atmosphere, but we accelerate the concentrations of tritium through our nuclear testing in the 1950s. That got into the water cycle. It's now in our groundwater, and that can be used as a tracer because we know when it was first introduced, when it peaked, and when it started to really decline. The same can go with CFCs, chlorofluorocarbons. We recognize that CFCs are not good for the ozone layer. We stopped using that, and that can be used as a tracer. And there's a variety of other ones out there too. We have that really old water. The best method there is carbon-14, measuring that total organic carbon that might be in the water and using that as a tracer, or actually to quantify the age of it. But kind of the point is all of these tracers have various advantages and disadvantages. And really what you need to really gain confidence in your data is you need multiple lines of evidence that is kind of telling you the same thing. And so that's what's really important when doing these tracer work. So going back about, 10 or so years ago, Tony and I had these discussions of, could we use maybe, some of these herbicide products that haven't been used as a tracer? And what was really interesting is that when you start looking at the data, and this is kind of that aha, like light bulb moment, when you start looking at the data and you start looking at patterns in the data. And this is spring data. So this is from 4 different sites. And this is for Allachlor ESA, which I'll talk a little bit about in the next slide. But this is a herbicide product that was used extensively in the 1970s and 80s. And this is showing where we have some linear decreasing trend at Spring Creek Spring in Goodhue County. We have Burr Oak Spring showing a kind of an exponential kind of long tail decline. And then we have Houston County, we have Highway 76, and then Big Spring and Peterson Spring, where we see a linear increasing trend. And then for these 2 springs, we're seeing sort of like this nonlinear sort of pattern in the data. And again, this light bulb moment was that for these sites that are increasing, we have not, what's interesting about this data is that we have not used Allachlor for over 25 years. So that alone tells us that that water is much older than what we think it is. So a little bit about Allachlor. Allachlor, the trade name was Lasso. If you were farming in the 1980s, I mean, this was the product that you used. There really weren't any other products available other than atrazine. So it was used extensively. It was first introduced in 1969. It peaked in 1980, and then its use fell dramatically in the 1990s. And effective use ended basically in the early 2000s. The reason for that, it was pulled off the market. Industry said there's other better products out there. Let's voluntarily pull it out. There was concerns about it getting in the groundwater. And so it really kind of set itself up for kind of an ideal characteristics for using it as a tracer, because we have this well-defined pattern of the data. And we also know that the degradate of Allachlor is ESA, ethane sulfonic acid. And this has conservative properties once it gets into groundwater. So it stays stable. And there's various assumptions that have to be made with all this data, and that's kind of detailed in the report. But kind of the overall methodology here that we used was basically looking at the difference between the trends that we saw in basically the Allachlor usage data, and then looking at the trends in the chemistry data that we're measuring in the groundwater, and then measuring the difference between the slopes of those 2 lines. Now to do this, we had to normalize the Allachlor use first to get it on the same units. And then this sort of makes the assumption that we have linear relationships. And of course, we don't always have parallel linear relationships. So there's kind of other methods that had to be used to kind of find a centralized difference between these 2 data sets. This works fine for linear data, but nonlinear data, this does not work. So we had to use different methodologies for that approach. So this is the study area. It's driftless area. We have 30 sites. These are kind of what I kind of call our trees to help us better understand the forest. We have 30 sites. We have 30 springs and 30 well sites. About half of those were springs, half of those were wells. And we had 3 different age dating methods that we used. The Allachlor method was used on about half of those. The other half we used atmospheric tracer work that USGS did concurrently with the project that John Niebuhr was heading. And then some other funding that we had through MDA, and then using existing data sets from Calvin Alexander in terms of the carbon-14 data. So again, kind of setting the scene up here, the geology of Southeast Minnesota can be set up as kind of these 3 main areas. We have area 1, which is our extensive glacial till. We have area 2 and area 3, which is our basically the plateau divide between the upper carbonate plateau and the Prairie du Chien plateau. I'm not going to use those terms anymore just because how lengthy they are. So we're just going to kind of refer to these as area 1, area 2, and area 3. But this is kind of showing the distribution of these 13 study spring sites that we use to estimate the age of the water. So this is, again, that cross-section, the geology. This is the location of those springs as they're situated in those different geologic settings. And we can group those into those different categories based on their hydrostratigraphic position. So finally, after all that, we'll get into the results. So this is what we found as far as the age of the water for those 13 springs. Now, this is really where John and Tony come in terms of when you analyze the data, you kind of like what is making sense here and what isn't. And what really kind of plays into here is these data are sorted by hydrostratigraphic position, by, you know, that highest to lowest. And so you see there that those shallow springs are showing an age of about, you know, in that 12 to 15 year age. And then those deeper springs are showing upwards of up to 41 years in age. We can also layer in the depth of those springs, and this is just calculated by taking kind of the difference between the mean elevation within the spring shed area and the elevation of the outlet of where we're sampling from the spring. And we can show there that there's a very good correlation, you know, between the two. And we find that for every 10 years, or for every 100 feet of depth, we're gaining 10 years in terms of the age. And just to note, that's where Big Spring is. So we estimate an age of over 30 years for that particular site. So again, the residence time, we can now layer in the allichlor data, the ESA data. These are the concentrations. We're just looking at the middle 50% of the data. This is in parts per trillion. These are very small concentrations, but the pattern of the data really tells us a lot. It really helps paint the picture of how to understand this. So essentially what we're seeing is this wave of the higher concentrations are now into that deeper, into those deeper springs. If we could go back in time, if we had monitoring data that went back in time, likely that peak would have been, let's say in 1990, would have been closer on those shallow springs where we would have seen that peak. So what we're seeing here is that wave continue to move to the right into those deeper systems. And so now we can look at the trend data for those sites, for those allichlor data. And again, you can see that where we see the increasing trends on those deeper systems, we have Big Spring, which is at or near peak concentration, and we have all those shallow springs having a declining trend. So this is the point where we said, okay, could we use this to estimate what's going on with the nitrate data? So we layer in the nitrate data for these sites. This is what you're seeing here is the nitrate data tends to be highest in those shallow springs, around 10 to 15. And it tends to be lowest in those deeper springs. Not a lot of variability though. You see how tight those boxes are as we get in those deeper springs. So a lot less variability, a lot more variability in those shallow ones. But when you layer in the trend data, this is what we find. So all of those deeper springs are increasing by a rate of about 0.7 to about 4.2% per year. So it's increasing at a rate of about 0.1 to 0.2 milligrams per liter per year. So every 10 years, it's increasing about 1 milligram per liter. So not a very, very fast pace, but it's very strong and it's very consistent in terms of that trend. We did have one spring that was showing a decline, and our thought there is that that particular spring is kind of an upper water table spring, and we think that that could be related to precipitation. So that's kind of one data set, but what if we now combine that with other independent data sets? So we're combining this with not only the allichlor method, but also the atmospheric method that USGS has, which is a independent method that uses totally different math and sort of basis for it. And what's interesting is where we had trend sites and also age, we plotted this, and you can see here that as we go up in age, the number of sites that have increasing trend also increases. So this is the results across all those sites. And this is the age that we had in terms of the average age was about 27 years. And this is considered the modern age water. And I'll kind of talk about that a little bit. So the big challenge, one of the limitations of using allichlor or even CFCs or tritium is that data really only represents from 1950s or 1960s on. So we don't know because we know groundwater represents a mixture of ages, and we don't know what that contribution is from that older water. So what USGS does is for their sites, what they do is they use a lump parameter model to estimate that contribution from that older water. And when you factor that in, that water is actually a bit older. We're talking maybe 3 to 8 decades when you factor in some of that older water mixing that's going on there. And so kind of the bulk age would be about 48 years for that, for those sets of data. Now, what's also important to recognize is that there's also a group of data, and this is well data, where there's also much older water. And this is where Calvin's data, Calvin Alexander and Scott Alexander, they did a sampling of wells in 2018, or roughly in there, along with DNR. And they intentionally sampled wells that had no tritium, no nitrate, and basically anything that might be caused by us. And what they found is in all those wells, what we found when we kind of referenced that data and pulled that into our data set, out of 135 of those wells, the mean age for that water was over 7,000 years old. And that was using carbon-14 dating methods. So if indeed our water is several decades old in many of these systems, and some of it being even much older, it starts to help us paint that picture of how to then interpret it. So one of those things we can do is we can now start to reconstruct what was the land use back, let's say, from the 1920s on in Southeast Minnesota. We can also reconstruct what the nitrogen fertilizer sales were doing, going back in time. And so if we look at where a lot of these big changes were occurring, that was occurring in the 1960s. From the 1960s and 1980s, we were increasing our corn production, the number of acres in Southeast Minnesota, by 10% per year during that time period. We are also, of course, makes sense, right? We are increasing our nitrogen usage as well. And really, nitrogen fertilizer really didn't really come on board until after World War II. And my dad is 88 years old and still farming, still actively farming. And he remembers the day that he bought his first bag of nitrogen fertilizer, synthetic fertilizer. And that was in about 1959. And he said it wasn't until that point that we really started to use it. And so, and you can see there that pattern makes sense where we've seen a lot of that uptick. We're also still seeing some changes out there. We see in the 1980s, our soybean production really started to take off. And we are also still seeing to this day that our hay and alfalfa production is still going down. And that rate is about 2 to 3% per year. That's kind of for that older water, but what about that younger water? So when we talk about that younger water, we have to think about how do we interpret it in the context of the weather and the precipitation. We are trending wetter. We started really getting wetter in the south and the southern Minnesota starting in about the mid-70s. And that's continuing to climb. And I'll kind of give an example to explain that here a little bit. So switching gears, we talked about residence time, we talked about the springs. Now let's look at the stream data. So again, we find that dominant trend for increasing in our stream sites. This not only includes 21 sites in southeast Minnesota, but also includes 22 sites in northeast Iowa. They had a great data set where they've been sampling religiously for the last 20 years. Once a month, they take this nitrate sample. They had 22 sites. We were able to reference and pull that data in. So it's a great data set that we can reference and evaluate. But this is the point where I was like, well, what's happening in the glacial till area, area 1? Because I'm interested in that because it's a much different system. We have a much younger water. We have tile drainage. That water is typically very young, like within that year or within the last 2 years. And what we find when we pull that data in, so think of Mankato or think of South Central Minnesota, our extensive tile drained watersheds. We were finding 39% of those sites were decreasing. And then when we look at the last 10 years during this study, 2012 to 2021, we find that number goes up substantially. So it basically doubles in terms of the number of sites that have a decreasing trend in nitrate. So what do the data look like? I just pulled a couple examples. 7 Mile Creek in Nicollet County. This is a small watershed, about 25,000 acres. And then we have the Blue Earth, much larger watershed south of Mankato. And we see 7 Mile Creek actually across the entire trend record, it actually was kind of showing a slight decline in the nitrate, no trend at the Blue Earth. But what's really dictating likely the trend in 7 Mile Creek is that last set of data there. And if you just look at those 10 years, we were significantly decreasing those trends by between 5 to 7% per year, which is really quite remarkable. So is that because of practices that we're doing, or is that because of some other factor? Likely the dominant factor is the weather. And this is a good example of that. So what I did here is I pulled together, this is a heat map showing the orange warm color showing really dry conditions, the blue showing really wet conditions. And this is using data from NOAA. This is the Palmer Hydrologic Drought Index. And what's interesting, again, where you see more of that blue is starting in the 1970s, 1978 especially. Yes, we have these patterns of dry conditions, but nothing like what we had in the 1930s. And what's really interesting is when you look at 5 of the 12 wettest years in the past 128, they all occurred consecutively between 2016 and 2020. And we set records during that time period across the state. 2016 at Waseca, 54 inches of rainfall annual. That broke the record, the previous record. And then just 2 years, we smashed that record and went up to over 60 inches of rainfall, annual rainfall received at Harmony. And that's on par with Biloxi, Mississippi in terms of an annual precipitation amount. So really quite remarkable in terms of the amount of precipitation. So what is that doing? Well, likely what that's doing is it's diluting that nitrate. We don't have that buildup of the residual nitrate in the soil profile. And likely in these poorly drained watersheds, we have denitrification occurring. But what's really interesting, again, look at the colors. More blue in this very wet period in that south central Minnesota for streams for nitrate. But notice in southeast, in this area 3, regardless of the weather, the trends are staying the same. They're still increasing. So again, that's another piece of information that we can use that tells us that that water is much older water that has less influence from recent land use activities. So that kind of sums it up for the streams. I'm going to kind of talk about the well data now. And in well data, it's really quite complicated because it really depends on where you're at and what kind of well you have and how well is it constructed. So the best way that we found to kind of explain this is to run a few different scenarios. So if you're a well owner and you live in area 2 and you have a shallow well and you're above the Decorah Cummingsville Aquitard, this is what we are likely to expect to see in your well. We're likely to expect it's probably going to be a depth of probably about 150 feet deep. It's probably pre-1974 construction, meaning it's pre-well code. Probably doesn't have casing or grouting with it. Probably has high nitrate. We're probably going to have at least 4 milligrams per liter or more. And it's likely that that water is less than 20 years old. And we're not likely to see a trend in that water. It's going to go up, it's going to go down, but it's likely going to stay pretty much where it's at. So it's pretty much in a steady state with the current land use. We can have a well right next to that well that, let's say, is drilled down about 500 feet deep into the Shakopee right above the Oneota. And we'd expect it to be that about 500 feet deep. We'd expect that well to be cased and grouted post well code. And we'd expect to not see any nitrate. And that water is likely thousands of years old in terms of that age, the bulk age of that water. We can do the same thing in area 3. Area 3 is a little bit different because the main thing is in area 2, the well drillers know, well, because of well code, you actually can't drill in those areas because we know we're going to find high nitrate. So they're kind of required to drill below that. So one thing is you're not going to find as many wells. There's still wells that people are drinking from up in that area too. But where we find more wells that are kind of more susceptible to the nitrate is in this area 3. And especially in wells that are in the Oneota and into the Jordan. And so that dashed line there is kind of showing you kind of that area where we think that's where that nitrate is kind of moving through the system. And it's likely that we may see an increasing trend also in that location. It's not guaranteed, right? There's always going to be exceptions to this, but this is kind of in general a conceptual model of what we can kind of say. Now, in well E, that would be very similar to well B. where if you get below the St. Lawrence, it's gonna be, very low nitrate, non-detectable nitrate, especially if your well is cased and grounded. So now we can start to pull all that together and develop this conceptual model of how the groundwater looks in the southeast using that same cross-section. And so again, those lighter colors showing much younger water, the dark blue showing that much older water, some of it ranging from a few decades, some of it ranging 30 to 50 years, some of it ranging to thousands of years old. We can do the same for nitrate. And nitrate is sort of a reversal of the age, where we see the highest nitrate in that younger water, the lowest nitrate as you get away from those deeply incised valleys and we get below those aquatards. That's where we find that really much lower nitrate. So to kind of pull it together, that residence time, especially that modern fraction, that range from 10 to 40 years old in many of the shallow springs and wells to thousands in those deeper aquifers. And that younger water typically has elevated nitrate, but it tends to be pretty stable. And in some cases, we see it declining. Some of that decline we know is could be weather related. It also could be because of improved nitrogen management practices. So I wanted to make sure to mention there have been a lot of improvements over the years, especially the last 30 years. Plant genetics, how we apply our fertilizers, soil health programs, regulations, and so forth. The challenge, though, is sometimes a lot of this data is anecdotal. And so we need to continue to refine how we collect these data, but also, again, how do we tease this out compared to what the weather might be, sort of influencing our data on. For that older water, so many older water sites, we find that nitrates were much lower, but the levels are slowly increasing, especially in those spring and stream settings. And the main point here is that this trend is going to continue. It will not stop. And that will not stop until it gets to an equilibrium with the current land use. So, and this is especially the case in Area 3. So with that said, I want to kind of just emphasize the point that it doesn't mean that we just throw our hands up and we can't do anything about it, right? We know that the practices that we can do at the field scale, we know that they can work. Just how long it may take to see that effect, that's the complicating factor. So I kind of want to end here with now talking about the field scale and just kind of give some examples of some of the things that are going on in the Southeast to address this and to be proactive in terms of addressing this nitrate issue. And I've been lucky to be a part of this project. This started back in about 2008, early discussions about this idea of what if we could select a few small watersheds and just throw everything we have at it in terms of our monitoring, our interactions with the farmers and our stakeholders, and really kind of provide a good example of what we can do if we work together at this challenge. And this, again, this was back in 2008, we were having these conversations. And as a result of kind of a collaboration between a lot of different groups, this picture is showing one of our agronomists. It's showing about 4 or 5 of our farmers and our Soil and Water Conservation District staff and some of our Discovery Farms advisory team members. We meet typically twice a year and we talk about the data. We also talk about, what can we do to address some of these challenges. We could not do this without our farmer leaders. This is some pictures of some of them. And I'm just going to give an example of one of our farms we've been working on over the last 15 years. And the picture there is of Richard Johnson. And I'll kind of show a case study there. Another piece of this, we cannot do this without, is Ron Miners. One of the things that we wanted to do as a partnership was, it's one thing to do all this stuff at the field scale. How do we get it up to the watershed scale and actually get this to work? Ron, about 10 years ago, he said he was going to be retiring. And I said, Ron, if you ever think about retiring, you want to do something, let me know. And I was really lucky. He called me and said, yeah, I'd be willing to work part-time. We're able to line up some funding. And he works about 10 to 20 hours a week. And he's just one of those guys that he's really passionate about conservation, and he knows how to talk to people and farmers and landowners. And just done a tremendous job of working with our farmers and helping them make it easy, to get conservation on their land. And one of the things we really focused on was, we didn't go in there saying, let's tackle this nitrate issue right away. What we did is we want to get the low-hanging fruit, the stuff that was easy to do, and also something that the farmer was really concerned about too. And this is a good example of these concentrated flow areas, and this is very common in the Southeast. These are the conveyor belts that convey that sediment, phosphorus, and pesticide off of our fields. And so we really wanted to get those areas tackled, and Ron did a tremendous job of getting our farmers to do that. We're now kind of this phase 2, which is to get those farmers ag certified. And it's sort of a certification program that allows farmers to really showcase the good things that they're doing on their farms. And we're not just picking farmers that are already doing great things too, right? We want to get those farmers that are making some incremental changes that can get them in this program. And that's what Ron is doing right now. About some of his time is working with those farmers to get that stuff done. So that also opens the door to this idea of, now let's talk about with the farmers this menu of options that we can choose from that can maybe make a difference on their farm, and especially in terms of reductions. The challenge, a little bit of the challenge of this is from the Iowa Nutrient Reduction Strategy, the list of all the practices and kind of the effectiveness of different things. And the challenge with this is you can see the wide range of variability that we have with it. And also a lot of these sites are kind of drainage related, which doesn't really apply to Southeast Minnesota. But I'm going to show you an example of 4 areas of farm that basically implemented all these within the last 10 years. And this is our Johnson Rolling Acre farm. This was when I first started working with them, how they typically do their manure. So their dairy operation, what they typically do is they harvest that corn silage. They try to plant a cover crop out there, either aerial applied or with a maybe airflow unit when they're applying some of their fall fertilizer, their P and K. But the problem was with their system, the challenge that they were having is they needed to inject their manure into that. The challenge with that is it does a lot of disturbance to that soil. And this is in the fall. So you can imagine once you do that tillage, it's going to basically terminate the cover crop and not really do much for you. So we had, the other thing is it creates this sort of issue where we have just a lot of potential erosion and, creates all kinds of havoc, especially for grass waterways and creating these sorts of situations. And so they recognized they needed to kind of figure out a different system. We worked with them and did a demonstration, worked with the Soil and Water District. We did a demonstration of a low disturbance manure injection system that allows them to incorporate that manure, but also not do as much disturbance to that soil. I also said, it'd be great if you could get that alfalfa every so often in those rotations, because that can make a big difference. And that's something that they're already doing, but it's just sort of tweaking a little bit so they can get in the rotations on more fields, getting that alfalfa in there. And then the third component was, once we got that disturbance thing figured out, now that third step was, okay, how can we get that cover crop on there where we're going to get a lot of biomass growing out there in a short amount of time? Because with cover crops, it's all about the biomass, and that's what's going to give us our biggest bang for our buck. And so they purchased basically a vertical till system, and they put air seeders on that. And they used to be able to maybe plant like 200 acres of cover crops a year on their corn silage acres. They've now gone up to 1,200 acres of cover crops that they do. They can travel about 7 miles an hour across the field with this unit, so they can go really fast. And so I've been measuring the biomass on those fields. And when we first started working with them, it was probably close to 400 pounds of biomass if we're lucky. Now we've been at over 1,000 to almost 3,000 pounds of biomass out there. So really kind of change things around in terms of the performance of some of the practices that they're doing. This fourth one, this is an interesting one. We're able to get a grant through the Nature Conservancy and some other partners to demonstrate this technology. This is relatively new technology to the United States. This is a unit that actually mounts on the manure applicator, and it basically senses the nutrients in that manure as they're applying it. So they're getting real-time nitrogen, phosphorus, and potassium values. And The livestock industry has always struggled with this, especially with the manure and the variability. And so we're working with Melissa Wilson right now to evaluate the performance of this on his farm. But it really could potentially be a game changer in terms of improving efficiency. We have suction cup lysimeters installed on Richard's farm on a few locations. And this is just showing the nitrate values in those lysimeters kind of during the early stages. And then as they've been implementing these different practices, you can see that alfalfa by far had a huge, impact on those nitrate values. And then as we, I think, continue to get those cover crops established, I think we'll continue to see, improvements in those nitrates. They're still elevated, but again, we're hoping we can get that down even further with those practices. A practice that every farmer can use in the Southeast and anyone that has row crop agriculture is the right rate and time. And so we've been working with the university. I'm so glad to see Giles Randall here today. When I first started back in 1999, I first got to work with Giles, and we did some test plots in St. Peter, and that kind of got me thinking just how important the value of this data. And since Giles left, we got Jeff Betch, who's just been a tremendous resource to us. And about 10 years ago, I said, Jeff, is there any way we can get you to do more of these plots in the Southeast to get more confidence in us, in these recommendations, and in our farmers and our agronomists, and setting up these classic nitrogen rate response trials, and trying to find that sweet spot of where we're gonna get a good return on investment, but also minimize the loss to the environment. And we have these big meetings with farmers to talk about the data, but really the value of this is these small little work group meetings that we have with the agronomist and the farmer and Jeff, and just that interaction of that question and answer, and that's where we learn and the most, and in those kind of small settings like that. And we've incorporated that knowledge into our on-farm demonstration sites. And this is one of our tile sites that we have in Mower County. We have 7 years of baseline data on that site. And this is kind of what we were measuring for the nitrate concentrations. And the farmer was normally putting on about 175 pounds of nitrogen. Because of the data, we went down to 150 pounds of nitrogen in a corn soybean rotation. He also started to split apply, and he also started using the N inhibitor at that time. And this is what we were finding for the concentrations. We're seeing about 36 pounds per acre loss out of that field, and a flow weighted mean of 15. And then this is during that treatment period. And we do see a reduction. This is provisional right now, because I'd like to get at least one more year of data at this site to kind of have equal years of corn and soybean. But we have this 7 years, we're seeing a reduction in those concentrations. And when we adjust it, based on the flow and kind of normalize that, for those different weather conditions, we come up with this estimate of about a 22% reduction. One thing I kind of want to highlight, though, is that we still can have some elevated nitrate in those in a wet year followed by a couple of dry years. And that's exactly what we saw in 2024. And so, but overall, it's really interesting to see that we've kind of shaved off, some of those really high concentrations. And so we'll just continue to monitor to see if this, this pattern continues with these practices. The other thing I kind of want to point out is, during that baseline period, we had about 88% of the samples above 10. And then during the treatment, we had 43% above 10. So still, we're going to have samples above 10, but certainly there's an improvement there. Last, I kind of want to leave you with, those are just a couple examples, but there's just lots of other great examples that are going on in the Southeast right now. And I think really things are really just starting to kind of take off here, especially with trying to integrate cover crops out there. Olmsted County's got a great program that they've been using to basically pay farmers based on the performance of the cover crop. So if they're able to leave that cover crop out there a little bit longer, they get a better payment. So it's based on that performance. There's also examples of, individual farmers like Ed, who farms in Goodhue County. And, over the years, he's done a lot of demonstrations and a lot of research on his farm and really opening it up. He's got a field day coming up in a couple of weeks. talking about planting green, you know, and the trials and tribulations that go along with that and sharing that knowledge with his other neighbor farmers. And there's stories like Alan Kraus that is with the Rice Creek Watershed Project, and he's just done a tremendous job of working with a small group of farmers in a couple of watersheds where they have gotten over 1,000 acres in this little watershed to use cover crops. And they were seeing some really good results in terms of the water quality as a result of that. And then there's folks like Martin Larson, who wears a lot of different hats. He's a spelunker. He explores caves. He also is a feedlot officer with Olmsted County, and he's also a farmer. And he's a very interesting person to listen to and talk to. And he's a really strong advocate. He understands that really to tackle this nitrate issue, we're probably only going to get so far with some of these practices, and we're going to have to be thinking about, you know, how do we integrate other crops into that system? And one of the biggest ones is, you know, our farmers have a history of using oats in Southeast Minnesota, but we lost that over the years. And Martin is really trying to make those markets, create those markets to for farmers to make it profitable for them to raise oats and get another crop out there other than just corn and soybeans. And obviously that's going to have some benefits for water quality. So in closing, so it's challenging, right? It's complex, but that doesn't mean we throw our hands up and we don't do anything about it. It's really important to recognize that the collective efforts that we do today will help reduce nitrate loading to these aquifers. But it's really that next generation, right? That's what we're really kind of really trying to help. And so it will help us over the long term. I think it also really highlights, as our study has shown me, especially when I work with Tony and John, is that importance of collaboration, partnerships, and that interdisciplinary approach to address these complex questions and issues. So I said I'd kind of come back to this Big Spring. So if we had to make one little edit to this plaque, we would say that the water coming from Big Spring is likely a mixture of water that dates back about 3 decades. So that concludes, and again, thank you so much for the opportunity to be here. And if there's time, I'm not sure if there's time for questions, but yeah, I'd be happy to help.
Kevin. Questions for Kevin? Wonderful presentation. We also have people online. Yes. Don.
Yeah, so,